My talk today is called Laissez-Faire Analogical Change. I'd like to immediately apologize for bringing you a morphology talk to a syntax conference. Analogical change, very simply oversimplified, is change by analogy, which it's one of the classic modes of language change, along with regular sound change and borrowing and so on. It's often been very vaguely defined in history. Compared to something like sound change, it's very erratic and irregular, and it can be hard to explain, but it's often easy to identify. All kinds of likely unrelated phenomena out there have been called analogical change, but we'll focus on what has been called four-part analogy. This is something that you've certainly come across before, which is the idea here is you're filling in a form that you don't know, or by analogy. So if dog goes to dogs in the plural and cat goes to cats, then what should the plural of cow be? You would guess cows productively, right? And this is a change that happened in the history of English. It replaced an earlier irregular plural, kine, which was still around in Middle English. And this is really a lexical phenomenon. We can find somewhat similar things happening in syntax. So for example, with the double object construction, you can form double objects with verbs of sending. It's like to mail or to send. When new modes of sending information came into being in English, speakers also decided that one could use this in the double object. So you can fax someone an invoice, or you can text them a GIF or a meme or something. Just as another disclaimer, I think it is important to recognize that even four-part analogy is really a cluster of distinct phenomena. And it's probably caused by a cluster of distinct mechanisms. My goal here today is to clarify a baseline, and I'll get to what that means rather than trying to solve all kinds of analogy at once. I believe this will help us better understand what needs to be explained when and where. Many trends in analogy have been pointed out. For example, what has been called the conserving effect of frequency is the observation that high frequency forms are more likely to be irregulars than low frequency forms. This works whether you're looking at roots or individual inflections or whatever you would like. And this is a static description of a grammar, but it's likely to have diachronic origins. Also, various kinds of markedness have been shown to relate to analogical change. I put markedness in quotes because I don't want to define any particular type of markedness. So for example, high frequency inflectional categories are more likely to serve as the basis for analogy than low frequency ones, and less suffixed or more basic or other similar concepts generally correlate well with frequency as well. And these are also more likely to serve as the basis for analogy and maybe less likely to be overridden. Stepping back and looking at a higher system level, it's been observed that there are some further trade-offs, such as one between irregularity and paradigm size. The terminology here comes from Ackerman and Maloof, where they argue that languages can either have large paradigms, which they call E complexity, or they can have a lot of unpredictability or irregularity, which they call I complexity. And so in these plots from a different paper, they're sort of showing that trade-off with E complexity along the x-axis and I complexity along the y-axis. If you think about this and think of a language like Turkish or Finnish, which has very large paradigms, they tend to be quite regular. But in a lot of other languages in Europe, which have smaller paradigms, have a lot more irregularity, for example. So descriptively, there's something going on here. So a whole range of accounts have been proposed to drive these patterns, largely functional in nature and proposed by all kinds of very different sorts of researchers. So for example, there are people who proposed entrenchment in one form or another, which is the proposal that some sort of strengthened lexical representation or something like that makes a form more resistant to change, or some minimizing conditional entropy. So the claim here is that we are cognitively unable to handle large amounts of entropy, so we need a simpler system to avoid that. Or many other drives towards paradigm uniformity or predictability or confidence or reliability all have been proposed to account for similar patterns. So it's possible that they're putting the cart before the horse a bit, though, when dealing with functional accounts. And I would prefer to argue that analogical change is driven primarily by afunctional factors, which would mean that many observed trends in analogical change are epiphenomena. They may be descriptively functional or optimized, but that doesn't necessarily mean that they were created by a form of optimization. So they could instead be created by a process that is blind to these concerns. That's why I use the term afunctional. It's not necessarily anti-functional, it just doesn't care. So another way to put this would be to don't confuse the effect for the cause. So then we have a question, well, how much of analogical change can be handled in afunctional ways? To do that, we need some sort of null hypothesis. So here's a general idea, which it's really just that the property of the stimulus can drive these trends. And there are a few parts to this. So we know that data sparsity or input sparsity is pervasive at all levels. It's a really big deal when it comes to language acquisition. It's one of maybe the largest issue in language acquisition. From one reason to look at morphology for this, at least to start with, is that it's probably easiest to quantify the sparsity with morphology. The next is that language acquisition really is hard. We know that it would be impossible given what the input data looks like without a well-defined language faculty. But it's not like our language faculty renders acquisition trivial. It's still hard. UG only manages to get it to the point of tractability, really. And then many things that one might want to learn, language-specific things, are going to be rare or absent in the input. And this is, again, an empirical fact. But this means that then learners have no choice but to infer them, given what they already know, both from their language faculty and from their input. If this is true, then rare things will tend to be analogized away because they're less likely to be present in the input. They need to be inferred, when frequent things are going to tend to be more resistant, without necessarily relying on token frequency per se, for example. So I'm going to look at a couple measures of sparsity today. The first is paradigm saturation from Chan 2008, which is the proportion of a word's possible forms that are actually attested in some corpus. Our relevant corpus here would be the primary linguistic input that someone receives. So talking about nouns, for example, if the size of a language's paradigm, like defined extensionally as n, and the noun W is attested in some corpus in n of those, little n of those big N forms, it's just the proportion is the paradigm saturation. It's a similar concept. We talk about inverse paradigm saturation, where instead of asking how many inflectional categories is a given word attested in, it's how many words is a given inflectional category attested with. And this is also just a ratio. So if the perfect active indicative third person singular is attested with little v verbs, out of all the verbs in the input, that would be the inverse paradigm saturation. Now, these tend to be sparse, and they tend to follow long-tailed distributions. The most famous of these long-tailed distributions for language, and probably outside of language, is the Zipfian distribution, which says that frequencies are inversely proportional to frequency rank. So here, in this plot, just for raw lexical frequencies, the is the most frequent word in English. It occurs about twice as often as of, about 3 times as often as and so on. The effect of this is an extremely long tail. So almost all the words have very low frequency. This scales with the size of the corpus. No matter how big the corpus gets, you're still going to have this problem. You can't get away from it. Not all long-tail distributions are Zipfian, and what I'm going to say today doesn't necessarily rely on Zipfian-ness, but it's worth discussing. Here's a nice plot about Spanish lemmas, where the x-axis is lemma rank, frequency rank, and the y-axis is log frequency. And just to be clear here, log frequency means that the red points on this plot are the order of 1,000 times more frequent than the blue points. Not 10 times like it shows on the plot. So things are really sparse. So there are a bunch of things in language that obey Zipfian distributions, such as inflected form and lemma frequencies, and also paradigm saturations, which becomes relevant. So here are some numbers that I extracted from some corpora for verbs. All these corpora are nice because they're a part of speech tagged, lemmatized, and feature annotated, so I didn't have to do that. I looked at some child-directed speech and some not child-directed speech from the Universal Dependency Tree Bank. I've got some modern languages and some historical languages. The Universal Dependency Tree Bank was built for NLP purposes. So it's really fascinating to me that they have a Gothic corpus. It turns out something like 1/3 of all extant Gothic has been annotated in this way for natural language processing people. So if you look at, here I have the maximum saturation, mean, and median saturation in each of these. You see that for English, it's relatively high. And well, English verbs only have 5 forms at a maximum of 5 distinct forms. But for these other languages, you can compare the saturations. For most languages, the maximum saturation, so the verb that has the most forms attested, is under half. And then the median is much lower than that. So for Spanish and German, this is only a couple forms per verb are attested in millions of words of text. To visualize this here, these are these Zipfian distributions where the x-axis is the lemmas by frequency rank, and the y-axis, it's not normalized, so that you could see some number here. This is the paradigm saturation. And you see these follow these long-tailed distributions. It's worse for some languages than for others. And if you're looking at with a small monitor or your video is low resolution, you probably can't see. But for all of these, there's a really tall, narrow needle-like spike in the high frequency range. And so finish, I can't even see it on the monitor I'm using right now. It goes up to here. It just looks like white. So this is very sparse. Here's another way to read these plots. I purposely colored in under the curve here. So you can think here, the colored part, the blue part here, is the proportion of possible inflected forms in this language that are attested in this corpus. Then the white part is the part that exists that a speaker could generate but are not attested. So this really emphasizes how little we have to work with in our input. And for some other concrete examples, it turns out if you take 1 million words of Spanish child-directed speech, the word with the highest paradigm saturation is the verb for to look at, and it's under half. The median in child-directed speech is about 3 forms per verb, and in universal dependencies is about 1 form per verb. Then here's a plot of the percentage of verbs that are attested in how many forms in 3 different Romance languages, both in child-produced and child-directed speech. And in all of these cases, the overwhelming number of verbs are only attested with 1 form, and then some are with 2, and very few have the 6. And this is by person number, so 6 forms. What this means, and since these distributions scale, you will as a speaker of one of these languages, you will probably never hear most forms of most verbs in your entire lifetime, let alone while you're acquiring your language, which means that you have no option but to infer them via productive irregular patterns. Inverse paradigm saturation. For this, we find that some inflectional categories tend to be far more frequent than others. And I'll show you some plots. These are skewed, but they're not very skewed, but they're not Zipfian. Which forms are more likely to be attested are influenced by situational factors. So for example, in child-directed speech, it's often second-person singulars because people are talking to each other, while in other domains, third-person singulars are more frequent. Simple presents and pasts tend to be more frequent than other things, or whatever your language uses instead of a simple past or present. So taking Spanish again, the second-person plural, even in dialects that have it, is by far the rarest. And this tends to hold up fairly well cross-linguistically. And the second person plural imperfect subjunctive is just the rarest inflectional category in Spanish, while the third person singular, present, and preterite are very common. And so here, because I had the Gothic data, I looked at it. Here you can see the past third person singular and the past participle are by far the most frequent compared to everything else. For the languages I showed before, this is what you get. Again, see there, if you draw the box around it, you see this is less, these are less sparse, but it's still by far only a fraction of potential attested things actually are. So then, given that, here's an a-functional intuition for regularization, which is if true irregulars are lexically specific, so they're not generated by rule, they have to be memorized, which means you have to hear them to learn them. While regular forms are not lexically specific, they're generated by the grammar. So they can be inferred once the grammar is learned. You don't have to hear an individual irregular to learn it. You don't have to hear an individual regular to learn it as regular, right? But word frequencies and inflectional category frequencies are incredibly skewed, and most forms are not heard during acquisition, which means innovation is then going to be biased against rare phenomena. So innovations will tend to be regularizations, which is something that we do see in child-produced speech overwhelmingly. And so this gives us sort of an a-functional bias towards regularization among low-frequency items. So, for example, it's much harder to learn low-frequency irregulars than high-frequency irregulars, simply because they're not attested very often. And this exerts a diachronic pressure against low-frequency irregulars. And unmarked inflectional categories are far more likely to be the attested ones. So they're far more likely to form the basis for inference rather than being overwritten. So we don't see second-person plurals forming the basis of new third-person singulars. If anything, it's going to go the other direction. So then, well, it is true that token frequency correlates really well with these things. Like that's undeniable. That's just also a fact. So we can ask if token frequency is causal, because that's often what has been proposed in some guise or another. The thing is, token frequency is also highly correlated with both paradigm saturation and inverse paradigm saturation, which means that the presence of a token frequency correlation doesn't implicate token frequency per se. And the paradigm saturation is an empirical fact. It's just true of the data. I don't need a theory to, that's not a theoretical assumption. It just is. But claims about the cognitive representation of token frequency and their influence on the grammar or in the acquisition process are theoretical assumptions that do have to be motivated. They aren't wrong per se, but the empirical facts are right. So this gives us a sort of baseline. We would need to show an effect beyond the baseline. And using that data that I showed before with some of those languages, here you can look at paradigm saturation, rank and token rank, and you can, for nouns and verbs for Latin and Finnish, and you can see, well, these aren't straight lines, but they are clearly correlated. If we do it for inverse paradigm saturation, you get this. And there's no point running a statistical test on this. Like it's a line. You can just see it.
You have 5 more minutes, Jordan.
Okay, thanks. Further, there's this trend that larger paradigm size means more sparsity. So, and you can see the blue is decreasing here as you move to the right. And here, if I plot the data that I showed you before, you see this negative trend with paradigm size and mean paradigm saturation. So going back to the I complexity, E complexity trade-off, which is the trade-off between paradigm size and irregularity, as paradigm saturation decreases because paradigm size is increasing, there's less evidence to learn irregular forms, which means that I complexity necessarily decreases. We don't need to fall back on minimization of conditional entropy. That's emergent. So that's a learning story, not a diachronic one. So I just wanted to run a a little simulation for you. So say irregulars are introduced into a paradigm and they're roughly uniformly distributed. It was due to a sound change or something that doesn't pay attention to frequency. Will the frequency regularity correlation emerge? So there are some important facts behind this. Some of this was talked about in one of the talks yesterday, which is that children mature in communities and receive input from multiple speakers. The whole idea of generations is these big quantile things really isn't, big quantum things isn't really true, right? The population ages in a continuous pattern. We know that young children attend to sociolinguistic phenomena and that they attend to input in particular from older children who are slightly older than them and who themselves may not be linguistically mature. So we get variable input and not the entire input is from competent adult speakers. So that poses a little bit of a problem for the classic Z model here, which is, it's still a good model, but to be a little more careful about it, we know that speakers can draw productions from multiple grammars, like a competing grammars thing or a variational learner thing. We know that speakers are embedded in the community, so they're receiving input from multiple people. And we know that there's this, even by kindergarten age, like 3- and 4-year-olds are paying attention to children who are a year or two older than them. So the generationalness really isn't quite right here. There's an inner loop. And so highlighting the colors here, this is more of like a cyclic multi-Z model. And in my dissertation last year, I called this sibling induced change. It shouldn't be taken super literally, but I think it's a better name than cyclic multi-Z model. So we can implement this. Say we have a population of 100 speakers, the number doesn't actually matter, where the youngest speakers are still acquiring language. Every iteration, the community ages up, the oldest one dies, a new speaker appears, and the oldest young one stops acquiring. The speakers interact with some sample of other speakers, according to some distribution, which turns out not to matter much. Say there are 100 lexical items that we're learning, like a verb paradigm or something. These follow a Zipfian frequency distribution, and we sample 10,000 inputs at every iteration from the community. Well, we're very unlikely to hear every item because of the Zipfian distribution. And irregulars must be attested in order to learn them, right? I used the tolerance principle as a learning model here. The details aren't super relevant now, but I do have some extra slides if people want to talk about it during the question session. If you run the simulation where you're learning from other children and adults for several cycles, you can run this a bunch of time and average the results. What will happen? So here's the results. Remember that I started the lexicon with uniformly distributed irregulars. I looked at 10 and 20 of them. That turned out not to matter. And if you run it over time, you can ask how many of those remain irregular. So the x-axis is frequency, the y-axis is probability of remaining irregular, and the points are the things that were initially irregular. You can see if you're high frequency, you'll probably stay irregular. If you're low frequency, you're probably going to regularize. And if you're in the middle, who knows? I mean, different languages end up doing different things. And this is completely afunctional because the learning model here pays no heed to that. It's a very simple learning model. So for applications to syntax, just to end up, it's going to be most relevant. Oh yeah, the slides got mixed. It's going to be most relevant for things that are somehow lexical in nature. So for example, which verbs participate in the double object construction? There are certainly semantic patterns here that help us decide, but there are also plenty of exceptions, and there are exceptions to the exceptions. For example, the Latinates have exceptions. So you can think of these as irregulars in a similar sense to how we were talking about the morphology. The other is adjectival passives. I think I'm actually running out of time, so I won't talk about those. And then for my final slide, you should think of the frequency correlated regularization is the baseline here. Like the baseline isn't neutral really. So when you're building things, you should build them on top of this sort of, skewed baseline. We're building on top of a hill. And that's the takeaway.